Hello, calculus people. In the last case, we warm up with implicit differentiation on a circle. Now, quick check. What other conics do we have? Right. Parabola, ellipse, and hyperbola. How do we figure out the shape? We put the equation into standard form by completing square. So let's see an example. Implicit derivative at a point. If 4y plus 2y squared equals x squared, then find dy dx at the point 4, 2. Okay? At the first glance, this doesn't really look like a conic, does it? That's precisely why we need completing square strategy. I'd like to get through this model in roughly 10 minutes, so watch closely. I won't explain every step. We have already done this with the previous circle case, but I will post it on the blackboard so you can review it later, okay? First, rewrite it to y squared minus 4y gonna be equal 0, okay? And then it's the time completing square y plus 1, okay? And most important thing, this is gonna be plus 2 equal 0. All right, next, I'm going to subtract 2 both sides, okay? Yeah, close. That's the hyperbola, right? Direction. Let's see what happened. You need to divide by -2, okay? Then we will have over 1 minus x squared over 2. Ta-da! It appears hyperbola, okay? And the center at 0, -1. Vertical or horizontal? Fabulous. It's a vertical, okay? That means today we're going to tackle down the slope of the tangent line to this hyperbola at a spot 4, 2. All right, this is the key moment. I will walk you through the implicit differentiation step by step, so it feels manageable. Now, here's the game. So every time we hit a y term, the chain rule comes into play. So that's the rule where many people slip up, even teachers. So keep your pencil moving, but keep your head clear. So on the left side, the derivative for y is just a constant for dy dx, okay? So then what happened to y squared is just a constant 2 times the power rule, so brings down the other 2, giving 4y, okay? And then, since y depends on x, we must apply the chain rule. So it becomes 4y multiply dy dx. That's the step many people overlooked. Okay? On the right side, the derivative of x squared produce just 2x, okay? So simultaneously, we notice 2 is a common factor, all right? Keep in mind, fewer steps, fewer mistakes. I'm going to immediately cross out the common factor, common factor 2. All right. So right now, the dy dx, we can just factor out, right? And we will have 2 plus 2y dy dx gonna be equal to x. One more line, so dy dx gonna be equal x over 2 plus 2y. Since we're finding the slope at 4, 2, so let's just plug in, okay? 4, 2, okay? So we will have x gonna be equal to 4, okay? Y gonna be just 2. What do we have now? Right, this is gonna be 4 over 6, okay, which works out to 2/3, okay? Done. That's it. Implicit differentiation in just one shot. Just remember, every time if you see a white term, the chain rule has to come into play. If it's just a plain y, okay, plain y here, you just tack on dy dx and move on. Do that, and the rest falls into place. Honestly, the only way to master this is just practice. Lot of differential examples, different functions. It might feel weird at first, but you will get it. Don't stress. You are definitely not the only one working through this. All right, let's shift gears. My favorite GeoGebra hands-on. So 5 quick steps. You will see what we just worked out on paper come alive on the screen. Here we go. All right, step 1. Yes, we already know this is going to be vertical parabola, hyperbola. Okay. Step 2, you're going to plot the location for 2. Step 3, right, there's going to be a tangent line. Okay. Step 4, yes, we need the slope, d by dx. So GeoGebra feature this slope. We can just get the value decimal 0.67, which is 2 over 3. And lastly, watch how the tangent line swings as the point move along the curve. Okay? That visual should lock it in. Implicit differentiation isn't just a symbol pushing. It's a geometry in disguise. Okay? So as always, the virtual manipulative code is posted on Blackboard. so you can exploit at your own pace after class. Let's do the wrap up. What's the takeaway? Again, like a circle, a hyperbola is an equation, not a function. In Union 2, we focus on functions, where every input y produces a single unique y. However, with conics, one x input often corresponds to two y outputs. When you place the algebra side by side with the graph, it becomes clear. The derivative represents the instant slope of the tangent line at one spot. So next, we will move beyond conics. We will tackle a general polynomial relation and see how the implicit differentiation makes finding dy dx not only possible, but efficient. Nice work, everybody. We are building real calculus muscle here. Keep it up.